Welcome back to the second webinar of this sixth joint training in atmospheric composition, jointly organized by the European Centre for Monitoring Service, the European Space Agency, and the European Organization for the Exploitation of Meteorological Satellites. My name is Christoph Schröder from the University of Malaga, your moderator of today's session. Before introducing the speaker of this session, I just would like to refer to the text on housekeeping rules that my colleague Michelle Zeng from Climate Kick has posted in the chat channel, at least for the participants that connect via Zoom. Above all, I would like to highlight that we're going to have a presentation of 45 minutes, followed by 10-15 minutes of question and answers. And you can post your questions in the Q&A section of the Zoom call, from where we'll pick 4 to 5 questions and address them to the speaker at the end of the session. Back to this webinar session, I'm delighted to introduce to you Johannes Flemming, who will provide today an introduction to modeling and forecasting in the context of atmospheric composition. Johannes Flemming is a principal scientist at ECMWF, leading the reactive gases and aerosols aspects team in the research department of the ECMWF. Yeah, Johannes, it's a great pleasure having you. The floor is yours.
Yeah, thank you, Christoph, for the nice introduction. So today I'm talking about modeling and forecasting of atmospheric composition. And as you can imagine, modeling atmospheric composition, that's a very wide-ranging topic where people usually, need years to learn and to make progress. So in these 45 minutes, I can only touch upon a couple of things. I hope you still find this sort of interesting. And I'm looking forward to your responses and to your feedback and your questions at the end of the talk. So let's get started. First, I present you a rough outline of my talk. So I think a good start is to remind ourselves what the atmosphere is made of and why we are interested actually in atmospheric composition and why we are interested in forecasting it. And then the main part of my presentation will be to talk about the most important building blocks for atmospheric composition models, which are the emissions, the chemistry, and the aerosol condensation in the atmosphere, and then the removal of the matter by deposition. So this will be really the core of this talk. And at the very end, if I still have time, I will give you an example of such a forecasting system for atmospheric composition, which is the system I work on, and that is part of the Copernicus Atmosphere Monitoring Service. So talking about atmospheric composition, I think we all know that most of the atmosphere is made of nitrogen, 78%, and then we have 20% or 21% of oxygen, and oxygen, of course, is very important for life. We breathe it, and sometimes we say if we feel sort of tired in a room or there's not enough oxygen. I think that's actually not the case. There's probably just too much CO2. So 20% of oxygen is really what we have. And then there are a couple of noble gases, which are also there sort of in the order of magnitude of a few percent. In terms of the meteorology, the most important species is, of course, water vapor, which forms clouds and precipitation. And this content of H2O can vary sort of in the range of 1 to 2%. So that's sort of, roughly speaking, the main components. But of course, if we talk about atmospheric composition, we mean something else. And we really zoom in now in the remainder 0.5% of the constituents of the atmosphere. So basically, what we do here is we calculate how many parts of a certain molecule is there compared to a million of molecules. So 1 to the power of 6 when we talk about parts per million. And if we zoom in into the concentrations, we find that the next most important species in terms of concentration is carbon dioxide. I think we are all familiar with carbon dioxide. I just updated the number here earlier this morning from 380 ppm to 420, which is where we are about now. And I leave it to you to calculate at what year roughly this graph was made when we still had a number of 380. And then again, there are noble gases which are of a similar sort of concentration range as CO2, like helium. And from an atmospheric composition point of view, then the next one which we're interested in is methane. And we have currently concentrations of about 1.85 ppm, and methane, of course, is an important contributor to climate change. But it's also, of course, involved in the atmospheric chemistry as such. So we are leaving now this level of where we talk about ppm and at sort of 1,000 in terms of the occurrence of the molecules. So now we are talking about one molecule among 10 to the power of 9 molecules of air. And then the next important one is hydrogen, the nitrous oxide, which also has a climate impact. And then we are coming to species which we would refer to as air pollution. So the most important here is carbon monoxide in terms of the abundance. And then we have a tropospheric, or we have ozone. And then we can do yet another step by a factor of thousands. And then we have lots of other species which are important for tropospheric chemistry or for stratospheric chemistry. And a couple of them are listed here in the air pollution context. The most important one, NOx or SO2, nitric acid, formaldehyde, and so on. So really, when we talk about atmospheric composition, we refer to over very large scale of or range of concentrations. And even the very, very small concentrations, when we talk about of the concentrations in the range of ppt or even smaller, they are not unimportant. Quite often it's actually, from a chemical point of view, the other way around. If a species has a very, very low concentration, and examples are here the OH radical, it could just mean that it's very, very reactive. So it has a very small concentration, but because it reacts so quickly and has an impact, therefore, on the tropospheric chemistry, its concentration is very low. And when we do atmospheric composition modeling, we really have to make sure we cover all these ranges and not neglect sort of species which have a very small concentrations. Okay, this is maybe enough to really raise your appetite for the topic, the wide-ranging and different concentration ranges of atmospheric constituents. Now, why are we interested in atmospheric composition? That's a trivial question, but I just wanted to go through a couple of aspects here. I think climate change is, of course, one big motivation, and the other is air pollution. Just to highlight the importance of the trace gases on climate change, I show here a graph showing the contributions to global warming for different gases as estimated in the AR6 assessment of IPCC. So carbon monoxide and methane, nitrous oxide, they're all known to be contributors to the warming and to the degrees that are indicated here, with carbon monoxide being the most important one. And then there are other species like sulfur dioxide, organic carbon, which have an impact on the aerosol loadings in the troposphere, the atmosphere. And overall, even so there's still a lot of open science questions, aerosols lead to a cooling because it reflects radiation back to space. So they also have basically an impact which to some extent counterbalances some of the warming that we see from the greenhouse gases like carbon dioxide and methane. So that's one important motivation for modeling atmospheric composition, is to understand the climate change driven by the trace gases, the greenhouse gases, but also the aerosols in the atmosphere. Another, and that's probably for this training course even more important, is the impact that trace gases or air pollution can have on our life. And what I show here is the impact that tropospheric ozone, which is an air pollutant, can have on plants. So on the left-hand side, you see a picture of some experimentation in sort of a controlled environment where soybean plants are exposed to ozone at relatively high levels, and we see that this leads to wilting of the plants, and it's obviously not very good for the yields. And you can do these calculations, what the impact is of tropospheric ozone on crop yields using models. And one of the results here is shown on the view graph on the right-hand side, where we see the yield loss, the estimated yield loss for wheat in different parts of the world because of tropospheric ozone, because of air pollution. And as you can see from the color range, this yield this loss in crop yield can range sort of up to 20%, which is really a very considerable number and is very important and has to be taken seriously. Besides having an impact on plants, air pollution, of course, also is really a severe health threat. What I show here in this view graph is from a paper that compares different sort of environmental factors that can impact our health, expressed here as loss in life expectancy. And overall, the authors of this paper and also other authors come to the conclusion that air pollution is really the main environmental factor in terms of reducing the years we live, and even more so than overall speaking about tobacco smoking. If you look into the plots on the left-hand side, the top, you see the different countries, and the redder the color, the stronger the negative impact of air pollution is. And we see that hotspots of a negative impact are over Asia, but also over Africa. And in the other panels, you see sort of the same plot, loss of life expectancy from other environmental or other hazards like HIV infections or conflict and violence or parasitic and vector-borne diseases. They all have hotspots in certain parts of the air, of the Earth, but overall, the loss of life expectancy up to 2.9 years globally is caused by air pollution. It makes it a very severe risk. And of course, maybe perhaps in contrast to climate change, reducing air pollution is not, it's difficult, but it's not impossible. So I think the efforts to have cleaner air are all worthwhile because they really lead to measurable increases in our well-being and in our health. So I think I touched upon a couple of these points already. So just one slide to summarize, why do we actually need to then model atmospheric composition? And by model, I mean sort of computer models that divide the atmosphere, the global one, or of certain regions into boxes, which calculate for each box the processes leading to air pollution. So we need these models, of course, from a very general scientific point, to test our theories and understanding of air pollution. So we have certain ideas, we put them in a model, we model them, we compare them against observations, and this will help us to see whether our understanding of the process is correct. So that's more sort of a scientific-driven reason why we need to develop models. But we also want to provide air quality information in area where we don't have any observations available. So you can maybe imagine that over certain parts we have more observations, over others we have fewer observations. So models give us the possibility, even though they are limited by the fact that they are models, to provide to users information about the air quality or the atmospheric composition, even if we don't have observations. And another motivation from a user-driven perspective is that we set certain aspects, like say the uptake of ozone by plants, which we would call a deposition, or other processes are not really well observed at all. So we really need models to describe these processes, to quantify them, and to understand them, and to find means to mitigate the impact. is a sort of a general point of view why models are important. A lot of applications that we do are related to air pollution forecasts, and that's making a pollution forecast for the next 3 days. And this can help people who are vulnerable, who maybe suffer from asthma, to take sort of short-term measures to make sure they are not exposed to air pollution events. But we also need to look into longer periods, because a lot of the air quality measures are not just short-term, but they have sort of a longer averaging period. For instance, the exposure to ozone or to PM 2.5 over a year. So this means we not just need to make short forecasts, but we also need to provide the numbers for longer or historic periods. Another motivation, which maybe is closely linked to testing our theories and understanding, is that practitioners who want to improve air quality by reducing emissions need to know what is the actual impact. So there might be different ways of reducing emissions. You can maybe introduce short-term measures to reduce traffic. You can, in general, try to improve the exhausts from sort of all the cars that you have in a certain city over the long term. And then you want to know what is the actual impact of these measures on air quality. And models can be very helpful to test different scenarios of emission reductions for their impact of air quality, and thereby helping to find the most efficient one or the most targeted one. And sort of a last point that I want to make here, where we also have a need for atmospheric composition models, that has to do with the observation itself. So some observations, like in situ observations, they probably don't need models directly, but sometimes it's useful to find out whether a very high observation of, say, carbon monoxide in a certain place was a measurement error, which was caused by some problems with the instrumentation, or whether there was maybe a wildfire event nearby which led to this high value of carbon monoxide. So models can help us to interpret the observations in a better way. And the second application in terms of observations is related to satellite retrievals. So as you probably know from the previous course, the satellites, they only measure the radiation, and you need so-called retrieval algorithms which help you to derive the concentrations which you are interested in this. And in order to do so, you always need, or you very often need, a first guess of the atmospheric concentrations, and they can be provided by models. So here, atmospheric composition models to provide priors for satellite retrievals is a further application of the atmospheric composition models. Okay, so I hope you agree that we do need atmospheric composition models. So let's have a look into the main components of what they are made of. But before this, I wanted to show just another slide, which is related to the fact that I mentioned before, that models can help us to provide information about air quality in areas where we don't have a lot of observations. And these could be actually areas where air pollution is very high. So what you find here in this scatter plot is the attempt to show how good the coverage of this PM 2.5, so that's small aerosol particles, which is a severe threat also for humans, is related to population density and also to the average concentrations. So on the y-axis, you see an estimate of the annual average concentrations. So the higher up the values are, the more severe the air pollution is. On the x-axis, you find how many PM2 observation sites, monitors you have per million people. So if you have a lot of observations, then your values are very much on the sort of away from the 0 point on the x-axis. And what we do here is sort of actually some kind of anti-correlation, that in areas, especially in Africa, we do have very high air pollution concentrations being measured, if they are measured, but we actually have a very small number of monitors. So this is, of course, related to, you know, the problems to measure air pollution and the cost related to it. But it really clearly shows that in places where we do have the most severe problems in terms of the concentrations, sometimes we don't have enough observations, and models can, to some extent, not to the full extent, of course, help to fill these gaps. Okay, so now we move on to understanding the processes that we need to consider for atmospheric composition modeling. This is a very busy view graph, and I'm sure you have seen graphs like this before. It shows the many interactions and processes that relate to atmospheric composition. So we have surface fluxes, which we call emissions, from various systems. We have the anthropogenic emissions from our human activity, from transport, from heating, from industry. But we also have emissions from natural sources like volcanoes or the soil or the forest. They all emit gases or aerosol particles into the atmosphere, and then they are transported, they are converted one in each other, and then they are also removed by dry deposition or by, if they enter clouds, by a wet deposition or water out related to precipitation. Some of these components, which have a very long atmospheric lifetime, also are transported in higher levels of the atmosphere, in the stratosphere. And here we have a very different environment. The solar radiation is much more, especially in the V range, much more aggressive, which can lead to very specific photochemical processes. So it's a very complex picture. Many aspects have to be considered. So let's put it in a more structural way, as you can see in the next plot. So in principle, we need to start with the surface fluxes, the emissions, they are transported. Then we have the chemical and the aerosol gas phase reactions in the atmosphere. That's the processing as part of the atmosphere. And this basically represents our atmospheric reservoir or atmospheric burns. And then if you would have continuous emissions, of course, the concentrations would keep increasing all the time. This is, of course, not the case. That's why we have these removal processes, and they are called the wet and dry deposition. And they return then some of the species emitted or some of the species which have reacted back to the soil or the surface of the airs. And on a global average, the deposition processes are of the same, or the amount of mass deposited is at the same magnitude as the emissions, because for most species, sort of, we don't have a continuous increase, but it's kind of equal concentrations remain over the globe. So that's in sort of in boxes what we saw before in this very sort of interesting picture. Let's go one step further by formulating an equation, and that's shown here. And this is the basic equation that is being solved in all chemical transport models. So we want to know what is our local change of the concentration, and this depends on various processes. So the first one is what we call advection. That is the transport by the mean wind fields, both the horizontal wind and also the vertical wind speed. And if there's a divergence of these fields or these fluxes, we do get a change locally. So more of, say, carbon monoxide is entering my box than it's exiting, and that's why the concentration increases. A second transport aspect is turbulent mixing. Some of you are probably familiar with sort of the theory behind it. The mixing depends on the state of the atmosphere. If there's a lot of wind shear, we have a lot of mixing, or if there are a lot of convection or heat fluxes that lead to a sort of overturning of the air close to the surface of the Earth. We have vertical exchanges by turbulent mixing, which are usually much stronger than what we have by the advection in the vertical direction. And the strength of the turbulent mixing is very often expressed by so-called exchange coefficient, turbulent exchange coefficients K. So the transport in itself does not change the mass, it just moves mass around. But the mass is changed by the source sensing processes that we need to consider. And I mentioned already all three of them. We have the emissions, we have the chemical conversion R, we have the deposition. So models of atmospheric composition now solve this equation for usually sort of a large number of different tracers. It could be 10, it could be 100, could be even more. So that's why we end up with a system of coupled equations. And the coupling between the different species comes mainly from this chemical conversion term, because the chemical reactions, and I will come to this, between two species will be a source for a third species, or the other way around, it will be a sink for those two species reacting. So the complications and also the numerical cost of atmospheric composition models comes mostly from the chemical conversions and the aerosol conversions. The emissions in itself, they are independent of the concentrations, but the deposition is dependent on the concentration of the species. So if you have a high concentration of the species I, which you consider, you usually also have a very effective deposition, because the concentration and the deposition flux are proportional. Okay, so the emissions. Again, that's a topic where many people that have worked on for many, many years. It's a wide-ranging topic, and we have emissions from a lot of different sources, and we need to do them justice in some sort of way. When we talk about emissions, most people probably think about anthropogenic emissions, which come from industry or power generation traffic. So basically our human endeavors on the Earth. And these anthropogenic emission data are sort of put together or are compiled in data sets which we call inventories. And people who compile inventories, they take socioeconomic data, like what was the overall fuel consumption in Germany in 1921, how many cars were there on the roads, what are the emission factors of each of these cars, and then this is all put together to calculate, say, the emissions from traffic. So emission inventories are always based on a specific year, and we need to make projections for the future, because this process of making the inventories is very time-consuming and cannot be repeated every year in sort of very close to near real time. And also different methodologies very often lead to different results, and I will show some of them in a second. Another important set of emissions are emissions from wildfires, so biomass burning from forests, and they are of course different in different parts of the world. Some of them occur as part of the natural cycle, how vegetation grows, like in Africa. Many are caused by deforestation activities. We now find more and more wildfire emissions also in parts of the world, like in Siberia or northern Canada, where we have seen them before, but not at the frequency as in the last or in the most recent years, because of climate change, because of the extreme and unusual heat conditions in those areas. So that's also an important aspect. We get our emission data very often from satellite observations, because satellites can either observe the heat produced by these fires, or they can see the area where no vegetation is there anymore, but only burnt areas. So there are two ways to measure or to get an indication of the wildfire emissions. Besides those two emissions, which are probably the most important one, we also need to look into emissions from soil and oceans. And here, the most important one is the suspension of desert dust by wind, but also sea salt is produced by sea spray. Soils emit NOx, the oceans DMS. So we have relatively sort of wide range of emissions also from natural sources, and even lightning, as you probably know, because of the extreme heat, is sort of a source of nitrogen in the atmosphere, which is important on the global scale. These natural emissions have a very strong dependency on the meteorology. I already mentioned desert dust suspension, which obviously depends a lot on the meteorology. And that's why we tend to model those emissions in the atmospheric composition model itself, and not to rely on inventories for this. And this aspect that we want to model the emissions as part of our modeling approach is also true for the biogenic emissions from plants of volatile organic compounds. So that's basically if you walk through a forest, so the nice smell of the trees, that's sort of one example of these volatile organic compounds. They also, as you can imagine, depend a lot on the meteorology, on the state of the vegetation of the leaf area index. And because they change so much with the changing environmental conditions, such as temperature and radiation, it's really the best to online them together with the other processes as part of the model. So in general, emissions are considered really the most important input parameter to these atmospheric composition models. So just, I mentioned these different inventories, which are based on socioeconomic data. That's just one example here of the different inventories for different years, showing the sulfur dioxide emissions over China from the 1980s until 2020, over India in the middle, and over Southeast Asia. So, and each of these lines, which we show here, is a different inventory with a different sort of method to produce the data. So we can already see that the different inventories have a rather large spread, so of say 50%, if you, for instance, look here over China. In the earlier parts of the period, we see sort of individual years where the emissions go up and down. But then for the later period, these emission values mostly follow sort of a straight line. And that's because when this plot was put together, we did not, or these inventories did not have real data about the different years. They just had to make a projection. And these projections, of course, can differ to a large extent. And it's over China, it was especially sort of important because of the very strong efforts of China, of the Chinese government, to reduce air pollution, which was a sort of a very successful effort. It is still ongoing. The emissions actually were reduced a lot, but a lot of the older inventories did not take care of this, and that's why they just continued sort of this increasing trend, which of course is not correct. And here, this is a sort of another example of the emissions that we need to model. I mentioned already the VOC emissions, and here we see a forest emitting isoprene and xylene and other components, and then they are processed chemically in the atmosphere by the interaction with the OH radical or by photolysis, which comes from solar radiation. And then there are different sort of products on the way to further oxidation. The most important one is the formulation of formaldehyde, which in itself can have an impact on the ozone, tropospheric ozone, but also on the carbon monoxide concentrations in the atmosphere, which then finally ends up being carbon dioxide. But the important point here I want to make is about the carbon monoxide. Carbon monoxide, as we know, is an important air pollutant, and we would probably mainly associate it with sort of incomplete combustion processes, So everywhere where we have fire, like in anthropogenic processes, but also in biomass burning, usually there's a sort of large amount of carbon monoxide emitted, so it's a tracer for combustion. But this chemical production of the carbon monoxide from formaldehyde, but also from methane, is actually on the global scale stronger than all the emissions together from the incomplete burning. So it's not so easy that carbon monoxide is just a cause of incomplete or a sign of incomplete combustion processes, but it's also chemically produced in the atmosphere to a very large amount. And here, that's further on the topic of using the emission online rather than using inventories. What we see here in this graph is sort of work done together at ECMWF between colleagues from KNMI and other institutions. So Vincent Heunen was sort of a major author of this work. When we switched from using an inventory for the biogenic emissions, so these were pre-calculated data, monthly means which we used, and we see here the isoprene emissions and the isoprene over South America and over Europe, and the orange line, which is sort of more or less a straight line, which is sort of monthly mean data, pre-calculated, and then we move to an online representation, the red curve, where we see much more variability, because we can now, in a much better way, simulate the impact that temperature and radiation has on the emissions in a much better way, and especially periods where we have sort of something like heat wave periods, where we have high temperature over a longer period of a couple of days with very much increased biogenic emissions, can only be modeled with the online approach. On the right-hand side, we see then the corresponding impact on something that we are very interested in and what we can measure. This is the surface ozone concentration in Europe. So on this plot, you see a time series over a whole year. And in blue, we see the observed ozone concentrations on the wool stations over Europe. And then we have two model runs. The green model run used kind of the static external biogenic emission data, which do not directly correspond to the meteorological events of the specific days. And we see that in July, there are periods where we had increased ozone values because of increased temperatures, and also contributing where, in these cases, the increased VOC emissions. And when we then use the online emission approach, which is shown in the red curve, we are actually able to reproduce these temporary peaks of surface ozone. So it's really important, and it was a very good improvement of our model, that we moved from using inventory data to a more timely simulation of the VOC emissions, because we could model air pollution events over Europe in a much better way. A second aspect which is important for the emissions is the description of the variability, and we can also here make improvements by describing better the variability of certain sectors coming from different indices and the weekly profile. So that's also an area where we can make a lot of progress by modeling the emissions better. So emissions is really sort of the most important aspect of things that we can do to improve our model. In the remainder of my talk, which I think is not so long anymore, I want to briefly also mention the chemical conversions. And atmospheric chemistry is, of course, a subject which is very far-ranging. Again, you can study it. It's very long. So I just want to make a couple of very general comments. So in atmospheric composition, we distinguish between primary species, which are directly emitted, and we have what we call secondary chemical species or secondary aerosols, which are actually produced in the atmosphere. And typical examples of the secondary chemical species are ozone, and probably even more important are the secondary aerosols like sulfate and nitrates, ammonium, secondary organic aerosols. They are all produced within the atmosphere, and we need to model the chemical and aerosol processes to make sure we capture these species, or we can produce them in the right possible way. The atmosphere, if there was no sunlight, would have a relatively sort of slow and you could even call it boring chemistry. But because of the sunlight, because of the UV radiation, photolysis of certain stable molecules takes place, and this then produces reactive species called radical, and the OH radical is the most prominent example because it controls really the lifetime of many species, especially methane, but also SO2. And I already made the point that the computation of the chemistry is really very, very expensive because we have these coupled systems of chemically coupled species, which we call chemical mechanisms, which are, from a mathematical point of view, formulated as coupled systems of ordinary differential equations, and you need very expensive solvers to solve these equations. Okay, what you see here is what we did recently in our model. Before we had a chemistry scheme consisting of many species, and then we had an aerosols model or approach consisting only of sea salt, desert dust, organic matter, black carbon, and sulfate. And they were run independently in our model. But we decided to introduce more and more the modeling of secondary aerosols, so of sulfates, linking it to the SO2, of nitrates and ammonia, linking it to ammonia from the NO2 and NO3 from the chemistry schemes, and finally secondary aerosols, linking them to the terpenes and xyloline of the chemistry scheme. So we have now in our model a system where we actually can't really distinguish anymore in an easy way between aerosols and chemistry. They're all coupled because of the importance of the secondary aerosols. I have now talked about the chemistry, again, very brief. I want to also mention with one slide to explain the basic principles of the deposition. Again, apologies for being very, very brief here. I just thought I need to mention it. So we discriminate two different ways of calculating the removal of species of matter from the atmosphere. We have what is called dry deposition. So that is the deposition on the Earth's surface. It could also be the vegetation. And the typical approach to model this is to calculate a dry deposition flux, which is formulated as the actual concentration in the atmosphere times a dry deposition velocity. So the dry deposition velocity depends then on the state of the ground, state of the vegetation. And many processes have to be included in order to calculate this correctly. And then there's another sort of group of deposition processes which are related to cloud formation and to precipitation processes. So there are basically two different ways how matter is removed by these processes. One is called the washout or the rain out, and that is caused by the interaction of matter, of gases with raindrops falling through an area where we have, say, increased values of certain trace gases or aerosols. The removal is then coming from the precipitation falling through. Much more efficient is what we call in-cloud scavenging. where there is more time for the matter to become part of the droplets in the cloud, and then the cloud, if this cloud starts raining, the species is in the droplet, it falls to the ground, and both processes are at deposition. Deposition modeling is really also an area which is very, very uncertain, and where we have a large divergence between the different models. I don't want to go into much detail, but I just wanted to sort of give you an impression where we are sort of where this modeling tried to position of ozone as one example. So these are plots of a recent paper by Clifton et al., which show different box models simulating ozone deposition velocities at sites where we have observations of the ozone tri-deposition velocity, which is shown here as black curves in the time series plots on the left-hand side, which show monthly mean values for 1 year of different places or different measurement sites like Borden Forest, Macbuster, and so on. So we do see the models sort of disagree to a very large extent. There is some agreement in the fact that in summer the deposition velocities are higher, but overall the match with the observation varies a lot. And it's not just that the models diverge when we look at the deposition velocities. It's also, and which is shown on the right-hand plot, if we show to the contributing factors, the tri-deposition velocities are calculated from different processes which can have a different weighting. So either the stomata, the particle processes, soil processes. And what we see here are from the different models, each representing a bar for 3 stations, the overall calculated mean tri-deposition velocity, and then the sort of different contribution of the different processes. So we see even so the tri-deposition value is in the end very similar, but different processes contribute for the different models to get this value. So the uncertainty is relatively high. Okay, so how can we improve atmospheric composition models? That's sort of now sort of a summary. And I think improving the emissions is always a very important way forward to get a better atmospheric composition modeling results. And we can do this by better modeling the emission processes or by having better inventories. But we also have a process which is called inversion of emissions. And you will hear more about this in Antje Innes's talk, the next talk in data simulation processes, where we actually use observations to constrain emissions. And this is an emerging technique which is very, very promising. Another way to improve results is to increase, of course, model complexity. But here we have to be very careful to really make sure we're actually improving things, because that's at least my experience. Improving complexity is not necessarily always the best way forward to get better results because of compensating errors, but still we are scientifically driven. So we do hope that better modeling of individual processes can lead to improved results. Not just the individual processes can be improved, but also the grid box resolution. And I will show just one plot what the impact of resolution is. We know from our NWP colleagues that resolution is very important. But beside these kind of more traditional methods to improve models, we have, of course, now the whole range of machine learning approaches to sort of get to improve our modeling capabilities for atmospheric composition. And here we basically pursue 2 approaches. One is to stay in this area where we put together sort of an atmospheric composition model, which consists of all the processes, but we just replace individual components, for instance, a chemistry scheme, with machine learning variant or emulation of this specific aspect. But there's also another school of thought which says, no, that's not the best way to move forward. we should just learn the results of atmospheric composition models directly without pretending to, model or emulate specific processes, but just to take a lot of results from atmospheric composition models and to make sure we can sort of start with the situation at a certain point in time and then make the forward projection using machine learning. So these are the two developments. And then the combination with observation, what we call in general data assimilation, that's also a very promising way to move forward. And Antje Ines will also talk about this. And another way to improve atmospheric composition models is not just to talk about the models itself, but also to find better application areas. So we keep the same models, but we try to make them more useful by talking to users and to provide sort of specific products for what these users need for their application areas. Okay, so that's just a snapshot showing, coming back to this point about the different resolutions. What you see here is global model resolutions carried out at different spatial resolutions where the grid box size varies from 80 kilometers to 9 kilometers. If you look sort of at the global scale, the picture looks relatively similar. If you zoom in over Europe, you see a lot of more detail appearing in the very high resolution simulation, but overall the picture is relatively similar. And if we then compare this with observations, we see here the bias over Europe from different model runs with a different resolution. Overall, the RMSE error is similar between the different resolution, but maybe we can see that going to a 9-kilometer resolution leads us to a small or to some improvement in RMSE, which is fine. But we also have to look at the cost, and the cost increase is really, substantial if you go to these high resolutions. So it really has to balance carefully the benefits against the costs. Okay, do I still have some time left, or should I close at this point? That's just a summary again of the different components that we need. We need emissions, we need weather fields for the transport, we need observations, we need numerical models. These are then put together to air quality forecasting information system, which provide forecasts for the next days, which look backwards over longer periods, and which help us to understand processes better. And with this, I want to finish, and I'm open for questions if there are.
Yes, thank you very much, Johannes. Many thanks for this very comprehensive presentation. It's a pity not to go into more details for some of these aspects, but possibly, open the floor for questions and comments by the audience. I see that there's one question already in the question and answer section by Abhishek. I just read it out loud. This is regarding biogenic emissions. So does new biogenic emission have impact on organic aerosols too, apart from ozone?
Can you repeat the question, please?
Yeah. Do new biogenic emissions have impact on organic aerosols?
Yes, they do. I mean, the secondary organic compounds, they are produced by sort of gases which can be emitted by sort of human processes, by anthropogenic processes, but also by the biosphere. So we do see an important impact of the biogenic emissions on the formation of secondary aerosols, and that's actually was one of the motivations why we sort of increased our efforts in our own model to have these emissions online, that we have a better sort of description of the variability of the respective emissions.
Great, thank you very much. I don't see any more question from the audience. Ah, yeah, there's coming in one. Yeah, from Bertrand. Please, would you like to elaborate a bit more on the gas aerosol interaction and conversion?
Okay, again, that's a very wide-ranging topic. I mean, traditionally, I think there were global aerosol-only models which focused on desert dust, sea salt, biomass, burning organic matter. But the more you are interested in capturing the impact of human activities, you have to dig deeper into the secondary aerosols like nitrates, sulfate, of course, ammonia, but also the secondary organic compounds or secondary organic aerosols, which according to some measurements can make up to 50% of the measured PM2.5 values. So it was clear that just relying on the more traditional focusing on primary emissions aerosol modeling on the global scale was not enough for our model. And we had to introduce this link between the chemistry scheme, where the precursor emissions in the gas phase were already accounted for, but we didn't have that in place. And then there, of course, sort of the gas phase and aerosol partitioning is a complex process where we have specific modules for this. It's called the EUMETSAT module, and this sort of describes the equilibrium concentrations between the gas phase and the aerosol or the solid phase, considering processes not just in the dry air, but also into droplets and the wet chemistry, which is also an important pathway for the processing of the gas species into secondary aerosols.
Wonderful. Thank you very much. And almost a final question by Hamid. Does coupling weather prediction model with atmospheric composition model has some impacts about exactitude or uncertainty, I would say, of weather parameters prediction, or is important just when it comes to climate studies at large scale?
That's an interesting question. It would be a talk in its own rights. Of course, we do know that, as I started at the beginning of my talk, that aerosols have an impact on the climate, but they also have an impact on the weather, which we try to capture, but it's more difficult to do so. So the impact would come from the direct effects, so from inducing radiation, but also, of course, from the indirect effects on the cloud microphysics, where the different aerosol loads lead to a different formation of clouds and different precipitation rates. So we do see in our system at ECMWF, where we have for the CAMS forecast at the lower resolution, a coupling between the prognostic aerosols, so the aerosols really which are valid for a certain point in time, which have seen the actual emissions of wildfires. We do see an impact on these 2-meter temperatures in terms of when very strong plumes occur. These very strong plumes can come from biomass burning or from Sahara dust. But sort of one AOD unit, so if you're familiar with this, roughly corresponds to a temperature decrease of 1 Kelvin of 2-meter surface temperatures. But because in numerical weather forecasting, we always initialize our forecast with the recent analysis, with the recent observations, there's not so much time for these impacts to develop. So that's why the signal for NWP applications is sort of closer to the noise and more difficult to really extract. So that's why currently we can only show the positive impact of coupling atmospheric composition and weather forecasting for strong events, but not sort of on average for longer periods.
Wonderful. Thank you, Johannes. The last question I would like to still take by Hannah Jonas, which also links a bit to the tomorrow morning's session on data assimilation, I would say. So Hannah asked, which building block do you think is currently most promising to improve the comparison between modeling and observations? And example, extending chemical reactions using machine learning, improving emission data sets, etc.
Yeah, I'm a bit old-fashioned in the ways that I still think the emissions are the most important thing that we need to improve. And I do see a lot of potential in these inversion methods, where we basically use satellite data to have sort of constrain the emissions sort of in a top-down approach. So that's, I think, a very promising aspect where we can make improvements in the future and already have good results. This is developed a lot for sort of greenhouse gases, because here the monitoring is really important, but the same techniques can be applied for more short-lived species like NOx, which are important for pollution. I also hope that in the future, you know, with our increasing knowledge about activities, I mean, I just sort of thinking about Google knowing all about where cars are moving, that if we can sort of harvest this information in a good way, that we could maybe also come up with more timely or emission estimates, which would be then helpful for near real-time forecasting. That's sort of still something for the future, and it might be more important for the regional or city scale modeling, but it's, I think, also an important aspect, because this information is there, it just needs to be used.
Yeah, wonderful. Thank you very much. Yeah, Johannes, thank you very much again for your insightful presentation, for the replies. And yeah, dear participants, many thanks for your interest, for your active participation. The series of webinars continues tomorrow, as I said, so tomorrow morning at 9 a.m. with a presentation particularly about this issue of data assimilation, the data assimilation basics by Antje Ines from ECMWF. Yeah, see you tomorrow, and goodbye. Have a nice afternoon.
Thank you.